So when it comes to high performance computing and the I/O path in HPC, the critical thing is performance. And Lustre is a file system that is tailor-made for high performance computing workloads. Its genesis is in HPC, its focus is on HPC, and so maintaining and extending leadership in performance for storage is really the core of Lustre's aspirations, if you like, and that's the community aspiration. And what's interesting is that HPC is not a static environment, the workloads keep changing, and HPC is being applied to a wider set of application problems across a wider set of organizations and industries. And so the demands on the storage and on the HPC platforms as a whole are actually quite dynamic. So beyond the basic sort of core tenets of maintaining performance and extending scalability, there are other aspects coming in, other requirements coming in for Lustre as well. And so we start to see requirements around RAS, around features like replication and sort of data management, lifecycle management, as well as different types of performance problems like small file I/O and so on. And the Lustre community is responding to that demand. Where do we start? So Lustre 2.8, just to give a recap of what we've been up to in 2016. Lustre 2.8 came out earlier this year. It's an important milestone release as it concludes a lot of multi-year project development, particularly around the multiple metadata server support, DME. That project officially sort of concluded with the release of Lustre 2.8. It's now a feature complete part of Lustre. And this gives us our metadata scalability, and that means more inodes and more performance for metadata-oriented workloads. The other major multi-year project that's complete now is the LFSCK. Now, if you've got any kind of real sort of long-term background in Lustre, LFSCK used to be this horribly laborious offline consistency checker. It was a bit of a gull to work through. But this LFSCK is an online checker. So this is a file system consistency scrubber that runs while your file system is active and has a sort of minimal impact on your runtime environment. And it means that you can check for data integrity features and so on, and data consistency in the file system without incurring an outage. We also put some work into RPC scaling on the metadata. This means that the creates and deletes per client scale now much more significantly than we used to in the past. And then there's a lot of things happening around security. So fixing and patching up the Kerberos support in Lustre so that it's now functional. And that gives us Kerberos-based authentication and authorization functionality, as well as optionally we can enable the encryption features as well for network-based encrypted communications. And then SE Linux support, there's some preliminary support for SE Linux on the Lustre clients now as well. And we'll spend a lot of time on this. We present this breakdown of contributions in Lustre pretty much in every one of these kinds of updates. I think the thing I wanted to highlight here is that community participation in Lustre development has increased significantly release on release. So if you compare this chart to the 2.7 chart, you see that contributions from organizations outside of Intel has increased quite a lot. It's a trend that we find very encouraging and hope that will continue over subsequent releases as well. This is very healthy development for Lustre as a community project. So next release of Lustre is 2.9, and it's...
Who was the second biggest contributor?
Pardon?
Who was the second biggest contributor?
Oak Ridge National Labs this time around. But we've also got contributions from, as you can see, from Seagate, ANU, and DBM, and Crane, and so on. So there's a lot of contributions coming from right across the board now. The 2.9 release is actually due out very soon. It's going through a bunch of testing at the moment, and we're just ironing out the final bugs and blockers, and hope to see a release shortly. And that's all I wanted to say on that. It's due out pretty soon, so we're quite encouraged. Again, there's some more security work going on here with the node map support. This allows you to map UIDs from different realms into the local realm, so you can say, well, is this UID on site A matched to this UID on site B, and we can use that to sort of provide more global access control. This is very effective. It's very good for campus-wide operations or multi-site operations. You can also restrict access of node maps as well. Shared secret key encryption is an alternative to Kerberos encryption. It's much simpler to implement, providing an equivalent level of security. But the idea with SSK encryption is that it sort of complements Kerberos. You make a choice about which one is most suitable for your environment. One of the challenges that the developers of this feature at Indiana University found is that when they're working across multiple realms, that coordinating Kerberos cross-realm authentication was very challenging. And so it was a lot easier to just bypass that and spend several years writing an alternative piece of code to get around that problem. So when you're dealing with wide area networking and cross-realm client-managed, then the SSK is another alternative to consider. Sub-directory mount extension landing for that coming in place, so you can actually isolate past the namespace to a client, and then some work around an F-advise equivalent feature for I/O hinting in Lustre, and then large block I/O support as well for large-scale streaming I/O.
How large is large?
I think it goes up to about 16 megabytes IOs, something like that sort of range. So those are the releases that we have planned in 2016. So that's the outlook that we have the most immediate confidence on. But we're also behind the scenes on that. There's a whole bunch of other work that goes into a release. So Lustre supports multiple different types of backing store. It supports two at the moment. It supports the EXT-based backing store, and it also supports ZFS backing store. And Intel and Lawrence Livermore National Labs have both been working very hard on ZFS improvements. Improvements in being able to transact larger block sizes out to disk, improved file create performance. So if you're using Lustre and ZFS today, you'll see that metadata creates and deletes are a lot lower than their sort of EXT-based equivalents, and we've put a bunch of work in there to improve that. And the improvements are dramatic, and ongoing changes in subsequent releases. And we're also working on snapshots for the whole Lustre file system. So you can use ZFS to coordinate snapshot of your Lustre file system. In the ZFS code itself, we've made a bunch of really interesting changes. The ones I'm particularly interested in are that there are two new storage classes for your ZPROs. So ZPRO is a collection of storage devices in Lustre, in ZFS. And within that, you define volumes. And the volumes can be things like, they can be sort of RAID 5, RAID 6 equivalent layouts, they can be mirrors, they can be concats, you can do what you like. And what we've done is we've developed two new classes. There's a metadata class, which means that the ZFS metadata, as distinct from, say, the Lustre metadata, the ZFS metadata can be separated onto discrete devices. So that means that this really small, random, sort of very, very transactional high IOPS I/O can be segregated onto a device class that supports that more effectively than, say, a spinning disk. It also means that you're separating I/O so that your sequential I/O and your random I/O are kind of less contended. The other major feature here that we've got is parent AD cluster RAID support. So this is a brand new development in ZFS, and I don't believe that there's another ZFS implementation that has this, at least not yet. So this is really exciting stuff. And that means that, well, the key benefit for parity cluster RAID is reduced rebuild times from a degraded state to an active working state again. So if your disk fails, you can rebuild the array with a replacement disk far more quickly than with traditional sort of RAID 6 or RAID Z2 kind of methods. Sorry, I keep looking up there when it's up here. So data security, so a bunch of work going on here. So we talked a little bit about shared secret key cryptography. So this is RDMA and TCP/IP based encryption. So basically it happens at the LNet level rather than at the wire level, if you like. And then some improvements on the client authentication. So Indiana University has been doing work on shared secret key cryptography and roadmap support. And then we've been seeing some work coming in from DDN around subdirected mounts and further isolation of the file system. We're also looking at things like container support as well, and the implications of using containers with HPC and with like Lustre storage. On the networking front, Lustre networking protocol is pretty stable. It doesn't really change very often, but when it does, it's usually because of fairly dramatic leaps in technology or capability. So it's a pretty stable code base, but there's been some really interesting developments in storage fabrics, or sorry, network fabrics, and we've improved the support for those fabrics in LNet. So that means the MLX5 based EDR and LNOX IE stack, as well as Intel's on-the-path architecture. So they're both first-class citizens in Lustre networking and give you, dramatic improvements in throughput. The other bit of work that has been going on is support for multi-rail network topologies in the LNet protocol. So this gives us load balancing, aggregate throughput performance improvements, but also gives you, by default, essentially failover capability in your fabrics as well. So this is quite a significant improvement that Intel and SGI are making. So this is where we start to get into the more future-looking parts of the product. Data and NDT is a feature in development to improve small file performance, principally. The idea here is to allow small IOs to be transacted directly on the MDT, rather than having your metadata transactions going through one set of protocols to one set of machines, and then all your actual data transactions going to another set of machines. If the IO is small enough, it makes sense to try and consolidate that into a single RPC rather than into multiple RPCs. So the idea here is to give you a sort of net improvement in small file performance particularly, and then segregating your IO as well. So if you're doing mixed workloads, and you've got small file, 4K, 1K, horrible IOs like that, and they're competing with large streaming IOs, then you've got a whole bunch of seeks going on your object storage servers, and it's a mess. So what we want to do instead is provide an opportunity to separate the small IOs from the large IOs. And data and NDT is one of the ways of doing that, as well as consolidating the RPCs so there's less latency overhead and less communications overhead on the fabric. And this continuing in the theme of file layout and optimizing the use of storage, we've developed this capability called composite file layouts. And this is it's a shim inside the IO stack to allow you to define different ways of laying out the data, other than just doing a fixed sort of stripe. So in Lustre today, everything's essentially RAID 0 stripe. You write your data out to one or more objects in a fairly even pattern. And there's that gives us great opportunities to maximize bandwidth across the infrastructure. But it doesn't suit all workloads. And there are a lot of sort of newbie mistakes that happen when you start to come into HPC environments with parallel file systems. And one of them is that you set a stripe pattern of like the entire population of your object storage servers for a file that's only going to do about 1 megabyte worth of writes. Or the inverse, where you write out a terabyte of data to a single storage device. So the idea here is, let's try and come up with a sensible default that accommodates both workloads. So one of the layouts that we're defining is a thing called progressive file layouts. And the idea here is to create a set of non-overlapping extents and define that as the file layout. And each extent has a different stripe pattern. So if you only write out a megabyte of data, you only allocate one extent, and let's go. We've defined that first extent as just a single stripe. That would be the norm. And if you write beyond the extent boundary, you allocate a further extent with a different stripe pattern to optimize, for larger IOs, and so on and so on. So in the example here, the first step, 2 megabytes, goes out to a single stripe, and then the next gigabyte of data goes out to 4 stripes, and then everything beyond that goes across a much wider stripe pattern. So you set that as a default on your directory, then you can quite safely mix your I/O workloads with, have different types of files written out to the same directory, and have confidence that they're getting a reasonably good default. And there's nothing, of course, to stop you tuning and optimizing, but out of the box, you've got a much better chance of making good use of your infrastructure investment. So the progressive file layout feature is in development. It's at a reasonably good stage of development, and we've had some good results from it. Moving beyond that, the layout that's of most interest to me, coming from an enterprise computing background, is introducing some kind of fault tolerance into the data and making that something that is explicitly defined in the Lustre layout rather than implicitly defined in the hardware infrastructure. And so that means introducing some level of redundant layout or overlapping extents into the file layout definition. And so there's a bunch of work being done in this space, and this is going to be several releases worth of development. The first release, we're aiming to have a sort of asynchronous replication mechanism where you write the data out, and then on file close, that triggers a replica job. And then beyond that, look at things like synchronous layout. And then beyond that, well, we'll see. There's a lot of possibilities that are enabled by facilitating this kind of layout pattern. And one of the more striking ones would be to be able to version your replicas. So you can actually keep a sort of version history in the different replicas. And there's a whole bunch of interesting sort of replication options in terms of migration and so on. But the principal thing here is to look at data protection and to have that choice being made available to you essentially at runtime. So you make this decision based on the job that you're running, based on the way that you classify the importance of your data, and the amount of protection you feel that this data needs versus another data set. So you don't have to mirror like temporary files. You just want to mirror your production results or the data that is the results of your analysis, the high value stuff. And you can make that decision per job, per file. So last but one slide. Just wanted to highlight that some of the community developers have actually been making contributions to the Linux kernel. And we've had a Lustre client in the staging area of the Linux kernel tree for some time now. And we've reinvigorated efforts to make the changes required to have that code migrated from staging into the mainstream kernel release. And in a recent Linux kernel release, the 4.6 release, 2 of the community developers ended up in the top 100 contributors for Linux kernel as a direct result of this effort. So Ola Drucken, who's the Lustre gatekeeper for the Git repos, he ended up being sort of in the top 3, top 5 contributors to the kernel sheet, and then we have James Simmons as well from Oak Ridge, who also contributed significantly into this code base. This is extremely encouraging for us. It makes it a lot easier to deploy Lustre in environments where they're not necessarily using Red Hat or CentOS, where using Ubuntu or Scientific Linux or one of these other platforms. And if it's part of the mainstream kernel, adoption is just way easier, it's way more flexible. Now, this is the client rather than the server code base, but the client is really where most of that focus has to be anyway. And this is the last slide, just to give you a kind of approximate layout. This is based on the Lustre.org roadmap. So if you go to Lustre.org and go read for the roadmap, this is the way the community is currently sort of visualizing or representing the release trees for Lustre. So, looking at over the next 18 months or so. Yes?
So how do actually people contribute to the code? So there are some, I notice there are some people that are already doing so, but if people are not contributed in the past, which branch do they start on and where do they actually add their input into?
I don't know the mechanics, but we make the contributions to master. So there is if you go to, again, if you start with the wiki pages, they have documentation about how to make contributions. And if that's not sufficient, then there is a mailing list, and you can discuss that there. So the Lustre Discuss mailing list is a great place to kind of say, I have a contribution to make, how do I do that? It's not that onerous. The process is more, you work in your own branch, and then you send your commits in, and the gatekeeper will put them in through the test. So there's a whole bunch of automation that goes into the testing process as well. And we use Gerrit to marshal that. But the actual mechanics, I've never actually written any Lustre code, so I'm not quite sure exactly how that works. But there's plenty of help available.
Hi, just curious about upgrades, whether or not the features that we're looking for example, in 2.10, and we're running, for example, 2.7, well, as long as the major is the same, are we able to jump straight from 2.7 to 2.10 when it comes out, or should we be following as they go for more incremental upgrades?
So this is, so the theory is that you should be able to make the major leaps. The reality is somewhere in between two. Generally speaking, making that leap should be fine. The only time that's ever really been an issue was when there was a change from 1.8 to 2.0 or 1.8 to 2.1. That was a much more difficult change, although it was fully supported. And the only reason I'm a bit cagey about it is that when we go through the test process, we test from the previous to the current, and we also test accurately as well, so we test the downgrade from the current to the previous. But we don't necessarily do like a multi-generational kind of leap. So we don't necessarily test from 2.5 to 2.8, but we will test from 2.7 to 2.8 and 2.8 to 2.9. Generally, I think most people don't see any problem with that. Thank you.
Hello. Will the newer version require different hardware if you're doing like background integrity checking? Is there going to be more CPU jobs running around on the Lustre infrastructure?
So the LFSEK stuff, for example, runs on the server side, so the impact on the client should be a lot lower, and we've seen a fairly, it's a pretty small overhead in any case, so I'm not sure what the numbers are, but they're in a small number of percentages rather than, it's not like it's a 50 or 60% burden here, it's more like 5%, 10%, that kind of thing. And it should be constrained to the server side as well, so there shouldn't really be too much of a client impact. I can imagine maybe latency impacts, but I haven't got any data for that.
And what about the IO performance, the changes to use SSD? Do you have any examples of IO?
So those SSDs generally benefit the metadata. It's random I/O. Metadata are effectively small random I/O and very transactional in nature, so they're naturally geared towards SSDs. And so generally we do see an improvement there in terms of IOPS. And actually there was a really nice presentation that either this year or last year at the Lug about the 1 million IOPS Lustre installation. It's essentially an all-flash Lustre. For whatever reason, their design goal was 1 million plus IOPS. And so they presented all the data on that and what hardware choices they made in order to achieve that outcome. On the object storage, it really depends on your workload, whether you would get the benefit from that. The object storage is nearly all kind of sort of streaming I/O oriented. If you had a random I/O workload, then you would expect the benefit there. But I don't have that data from us about that. I think the way Lustre tends to work, because you tend to work in a heterogeneous environment, or at least in terms of workloads, I would expect maybe if you use something like Cowe, then you could allocate Cowe to different types of workloads and say, well, this Cowe in this directory will take the random I/O over the SSDs, and this Cowe will take the rest. And that would be one way of managing it. I don't think there's like a holistic, let's do everything all flash all the time kind of solution.
Just to follow on from a question from Richards, the data on the MPT, is there any sort of notion as to the amount of data that they're expecting to hold into the future? Are we going to see basically the Lustre of the future being multiple MPTs and no OSSs?
So that's actually a really interesting question. One of the logical conclusions of this approach, this data entity approach, is that you might start with an entry level or very bespoke Lustre solution that's just the entities. And for certain workloads and for getting started with Lustre, that might be all we need. And that's theoretically definitely possible. I think there does become a limit where if you're writing out like terabyte and petabyte data sets, that you really want the bulk I/O performance of object storage. But we might see more and more segregation of the data and say, well, anything up to this kind of size, really, it doesn't make sense to even stripe it, so let's just chuck it here. So it's definitely a possibility that you could see file systems that are maybe dominated by a couple of entities, or maybe 4 or 8 entities, and then a small complementary set of OSSs for the more streaming-oriented workloads. That's not really been developed, as a solution. It's more we're looking at IOs files less than 32 megabytes sitting on the MPT. That's kind of the design pattern that we're aiming for initially. And then everything else would migrate onto the object storage. But there's also opportunities for your files to perhaps reside on both as well. So, there's a potential extension where if you take the PFL kind of model, that the first stripe is a metadata stripe, and the next extent actually migrates it onto the object storage as well. There's a bunch of possibilities, nothing that's been necessarily sort of nailed down as a solution design.
Sorry, just to carry on from that question, I guess is the next one, which is with your progressive file layouts, are you expecting the LDS to actually predetermine how it would progress from, say, just a small file, start at the MPT and then...
So initially, that's a good question. So initially the onus will be on the user to determine how they want to lay out their data. So it's very much the decision making is put into the application or into the user. So you'll define your layout of file create. The fundamental file create process doesn't change. The MDT determines the file layout when the file is created, or rather when the file is first opened, that's when the layout is determined. And then at that point on, it's static. So you can see in the first release that you have a static layout. If you want to migrate the layout to a different set of servers, you'll have to transact that yourself. And over time, we'll look at more sophistication in there, probably through a policy engine, through automation. There's things like the L-Advise tool where you can actually send hints to the metadata server and say, this is the IO workload I'm expecting, and then that can help inform decisions there as well. I think for certainly initially, we'll be looking at the user making those decisions.
Any plans on putting in policy groups based on directory configuration, something like that?
So you can set a stripe on a directory, and that becomes effectively the layout policy for the files within that directory. So that mechanism exists, and that won't change. It will just be enhanced. Beyond that, policy management, sort of information lifecycle management is delegated to another piece of software. So, for example, Robinhood is a policy engine application that does that sort of work for sort of HSM movies.
So just another question on the MDTs. The sizing, is there sort of any guidance with now looking at possible with the D&E side of things? What's the recommended size or the ratio?
Well, just purely from a D&E perspective, or
Yep.
yeah, it's not really.
Okay.
So it sort of depends on some of the technology choices you make. So for example, EXT4 has a 4 billion inode limit per run. So if you're going to go beyond 4 billion inodes and you want to stick with an EXT-based platform, then you're going to need to do something. There's two ways you can solve for DNE. You can solve it with the sort of remote directory support, which is essentially saying that this part of the namespace will be allocated by this MDT. And that's more, I think that has less to do with, say, your inode population and more to do with workload. So it might be that this is a small file-dominated workload environment, and therefore maybe even needs different hardware or different type of hardware to transact that. And so that would be how you would split up your remote directories. For Stripe directories, I think a lot of it comes down to how quickly you create delete files. They tend to be the limit. So if you are doing jobs that create 1 million files and you want that done in a few seconds, then you're probably going to have to strike that across multiple entities and size that. So it's very much workload dependent, and we're still at a very early stage in terms of finding the right design patterns for the different types of application workloads and problems there. So there's not really a fixed solution or architecture for that.
And I'll ask one more question if no one else is. The ZFS, I've noticed there's a bit of work that's happening in that space going forward. Is that a move away from EXT formats?
No, there's still work going on in EXT. It's just that EXT being more mature needs less work typically. But EXT is not going away. There are still some advantages to using it over ZFS, and particularly in terms of raw IOPS performance at the moment, there's definitely a distinct difference. But ZFS enables a bunch of extra data protection features, so it's quite attractive. But because it's less mature as a file system on Linux, it needs further investment. So that's why we're seeing more development happening there versus EXT. But we still have a bunch of guys writing code for EXT.
So those ZFS enhancements are going straight back into the ZFS on Linux
Yes.
project?
Yes. So we have internally at Intel there's a project called Cowe, which is a DOE proto-exascale procurement program. And we're working with one of the supercomputers at Argonne National Labs. And it's all very sort of ZFS oriented. And so there's a lot of work going on there to develop next generation Lustre file system based on ZFS and based on sort of their requirements there. And that's all being brought back into the open source community projects from which they're deriving their software. So that means Lustre and the ZFS project. The one thing I didn't actually explicitly talk about in the ZFS improvements is the management and monitoring improvements going in there as well. One of our developers at Intel has taken the Solaris fault management architecture, that means the component of FMA that deals with the ZFS file system, and has ported that into the ZFS management system in ZFS on Linux. So that's another thing that we expect to see coming out fairly soon as well. And that gives you a lot more visibility of when the storage gets degraded and automatically resilienting and all that kind of good stuff.
So just regarding, I know you can't promise anything, but the progressive file layouts, curious to know if you're looking towards folks being able to apply that retroactively, so that once the feature's in place, if they have a folder where the default set stripe is to non-stripe, will you be able to maybe LFS migrate it to have the new progressive file layout to existing data, or will it only be for new data going forward?
So you should be able to migrate the data. You're essentially just redefining the layout, so an LFS migrate should be valid.
Okay.
That would be my expectation.
Because I can see a lot of data that would be generated between now and then that I'd love to take advantage of that feature for.
Right, I mean, I will say that it's almost certainly you're going to have to sit down and troll your file system and say, right, this stuff is going to be migrated over to this new
For
layout.
sure. Yeah.
But my expectation would be that that would be possible.
Beauty, thanks.
Any more for anyone? Okay, thanks very much.
Thank you.